All right, everybody, this is going to be your final exam review, filmed and posted. So we're going to be doing the spring 2024 exam. So let's jump right in. Okay, so the first section of the exam is obviously the nomenclature section. So all you want to do is identify the highest priority group. So in this case, this is an amide. So write that down first. So the parent is an amide. And then you always start numbering at the carbonyl carbon. So this is 1, 2, 3, 4, 5, 6. So 6 carbon amide, that's called hexanamide. Very good. And then you want to label the substituents. So on carbon 2, we have, this is an amino group. So let's label this in red. And this here is amino group. And so whenever you're labeling this, you're going to call this 2. And then since it's 2 ethyls, it's diethyl amino. Since both of these groups here are amino ethyls. Okay. So that's that substituent done. And then you need to label the substituents on the actual amide nitrogen. So this functional group and this functional group are both the same. So this here, since it has a carbon in between, this is a benzyl group. And since there's 2 of them, we're going to call that N,N-dibenzyl. So you're probably wondering, why didn't we do NN for this amino group? And the answer to that is, and make note of this, only use N when it's the parent. So we'll see in the next example what that means. But you see here, this amide is the parent, so we'll do dibenzyl here, opposed to this is not the parent, so we're just going to say 2-amino. So when you put this all together alphabetically, you should say N dibenzyl. And then what's next? Ethyl amino, so 2 diethyl amino. And then the parent is hexanamide. So that's the first one done. Okay. So moving to the next one, again, identify the parent. So here we have an amino group, and that's higher priority than just an alkene or a benzene. So if we use this amino group, then we also need to label the parent carbon chain. So if you go right, you'll get 1, 2. So that'll be an ethyl, which is really short. But if you go left, and you start here, you can get 1, 2, 3, 4, 5, 6, 7, 8. So this is a much longer carbon chain. We're going to go with that. So if you label that, the parent here, for now we're just going to call it octane. There's a double bond, but we'll get to that. So that's octane. And then if we look at our amino group, you can see it's substituted on the right side with a 1, 2 carbon chain. So let's do the substituent red again. This is 1, 2. So 2 carbons, this is called ethyl. And then on the ethyl, there's this group, which it's a benzene, but as a substituent, you call it a phenyl. And then not only that, you have to specify where is the phenyl. So it's 2-phenyl. So the substituent is going to be 2-phenyl ethyl. Okay. Then we have to deal with the alkene here. So let's do the alkene in pink. So there's a double bond between 4 and 5. And whenever you have an alkene, you always give the lower number the priority for nomenclature. So we're going to call this 4-ene for now. Okay, so now if we edit all of our stuff, basically, let's fix our parent now. So it is an octane, but it's also an amino group. So we call that, you just put amine at the end. But in this case, we need to label all parts of it. So let's say 4-oct, and then this is the ene from the double bond. And then the amino group is on carbon 2. So we're going to say 2-amino. Let's do it here. So 2-amine. I'll put another dash. So this is also a note you can make between numbers and letters. Always use a dash. Okay. Except, there's one exception, except esters. And we'll get to that example. Okay, but let's keep working here. So 4-octene 2-amine. So that's the parent. And then the substituent, since the parent is an amino group, the substituent, we do treat it like an N. So we're going to say N, and then we say 2-phenylethyl. 2-phenylethyl. Okay. And then there's one more thing we're forgetting, and that's the stereochemistry of this double bond. So this is trans, but it's also, you can call this E. So if you remember EZ nomenclature for alkenes, this one is E, since these are opposite sides. So this is E. So if you put it all together, you'll get E, and then N-2-phenylethyl dash 4-octene dash 2 dash amine. Yeah, so that's the second one done. Okay. And then the last one we need to work on is, and this is a little tricky because off the bat it looks like an anhydride almost, but it's missing the oxygen here. So this is not an anhydride, this is actually an ester. So we're gonna box in our parent here. So the parent is an ester. So let's count it off, okay. So for esters, the rule is you start numbering at the carbonyl carbon of the ester and you move away from the O. So we're gonna number this starting here. 1, 2, 3, 4, 5. And that's the parent. So if we redraw this whole side is the parent. And then in red over here, this whole side is a substituent. So let's deal with the parent first. So the parent is 5 carbons. So what is that? That's pentane. But for esters, you drop the E and you add O8. So pentanoate. Right? And then on the parent side, you also see we have a ketone on carbon 3. So ketone as a substituent is oxo. So this is 3-oxopentanoate. So that's fairly simple. And then on the left side, whenever you're doing a substituent, you start at the carbon closest to the O. Go 1, 2, 3, 4, 5. So for the subs, it's also 5 carbons. So what is that? Pentyl. And then on the pentyl group at the 2 position here, let's do it in pink, this here. This group is called ethoxy because it's an ether, but as a substituent, you drop the ER from the ether and you make an ethoxy. So this is 2-ethoxy pentyl. And then there's one more thing. Don't forget here, there's stereochemistry. So if you label the priority of these groups, let's do it in purple here. This is going to be 1, and then this is going to be 2, and this will be 3, and the hydrogen is 4. So if you make your circle, if you start here, you go 1, 2, 3, 4. This is counterclockwise, and counterclockwise is S. So this is S, 2-ethoxypentyl, and then 3-oxopentanoate. So let's name this stereochemistry in the front, S, and then between numbers and letters, you put a dash, so S, 2-ethoxypentyl, and then for esters specifically, you don't put a dash here, so leave a space. And then you put the parent, so 3-oxopentanoate. And that's the last nomenclature done. So a few common mistakes that you might catch here is putting a dash here, so you will lose points there. And then a big one is this point here. You only use the N like modifier when it's the parent. So in this first case, just be careful, this is not the parent. So you don't say N-ethyl. You just say 2-diethyl amino. So that's all the nomenclature. You will have an amino question because that's from chapter 19. So be on the lookout for that. Facts, I think you won't have facts on your exam. So I'll skip this for now. But I will come back to it at the end. If you do have facts, you can watch that. But we'll go straight into the reaction section. So she is going to be very tricky with these. On the final exam, she always tests every exception, basically. So you have to really know your reaction sheet extremely well. So for the first one, we have a CN. So this is a nitrile. Okay. And whenever you hit a nitrile with acid and heat, this reaction is called the hydrolysis of nitriles. So all this does is it takes CN to a carboxylic acid. So carboxylic acid. So just draw your arrow and reaction 1. We'll make this CN into C, O, and OH into a carboxylic acid. Then reaction 2, PBr3Br2. So this one will take a carboxylic acid to a dibrominated carbonyl. So you'll see there's a common mistake people make here as well, and I'll show you. So sometimes people might jump the gun and just brominate the alpha carbon. So this is sort of acceptable, but since the H2O is a separate step, you need to also brominate the OH. So both positions get a bromine in this initial reaction. And then the third step, whenever you have a halide in that position, this will replace the halide and take it back to carboxylic acid. So that looks like this. And this bromine will stay here. And then in the last step, this is probably the trickiest one. So you see you have NH3 in a large excess. So you would imagine that would replace this and this. So the thing is, it will replace both of them, but the acid workup will take this back to OH. So I would make sure you know this reagent very well. It will replace both of them with the NH or NR group, but since there's acid, it's acid catalyzed, it'll go back to OH. So your final product should have a carboxylic acid. So the H3O plus is the indicator that you have a carboxylic acid. What the final product looks like this, and the NH2 goes here. And looking at this structure, for all you biochemists out there, this is actually an amino acid. This is valine, actually. That's pretty interesting, if you guys care. So, that's it for the first one. Yeah. Moving on to the second one. We have benzene with the halide. So a good test taking tip is whenever you have a bromine on a molecule, a lot of times it's a good leaving group and it's going to react to leave basically. So the first step, at a NH2 heat and pressure, this replaces halide X with NH2. So this is just a simple reaction of a benzene. So you should all be comfortable with this. Yeah. So the bromine becomes NH2. Okay, this next step is not that intuitive. So if you remember from last Tuesday's lecture, this reagent specifically, NaNO2 and HCl, this will take the NH2 to N2Cl with the counter anion, or the counter ion. So the benzene stays the same. This becomes N, triple bonded N, and then Cl with the counter ion. So an easier way to write this though is you can just do N2 plus Cl minus. But that's what it actually looks like. And then whenever you have this molecule, whenever you hit this with the CuCN, you end up getting a nitrile on the benzene. So this takes N2Cl to nitrile. So reaction 3, you're just gonna put a nitrile group wherever the N2Cl was, so Cn. And then the fourth step, this one should be very, very easy. Everybody should know LiAOH4 is a strong reducing agent. So this is going to take the nitrile down to amine. Very good. So your final answer should be CH2NH2. Yeah. Okay, so this one is fairly straightforward. Just be very careful with this second reagent and make sure you know it makes this ion here. Some other tricks that she might do, she could use different reagents here. For example, the tetraborofluoride, I think, BF4, to put a fluorine on the ring. But that's something you'll see in the synthesis, not really in the reactions page. Yeah, so this one's not that bad. Okay, and then we're going to get to the most dreaded reaction box, reaction 3. So in this case, this one is a little bit interesting. You notice that there is a symmetrical molecule here with 2 alpha carbons. Now, everybody by now should know this reagent is a strong base. So it's going to deprotonate. Now, looking at this structure, since it's symmetrical, it doesn't matter which side you go to. So for the sake of this example, I'm going to deprotonate the left side. So there's 2 hydrogens here, and this will deprotonate one of them. So this is like not the product of step 1 yet, but it's the first step. So let's draw this out. So H3CO, and then this is deprotonated. Then you have this structure in the middle still. So then you have a minus charge here. And then it's very, very important that you don't show this as the product of step 1, because this will react immediately with its own self, basically. And so how that works is, since you can form a ring here, if we number this as 1, 2, 3, 4, 5, 6, this can react with itself, and so it will close here, and you'll make a 6-member ring. And so this is the real product of step 1. So this is now where we'll put 1, and we just formed a 6-member ring. So let's draw that. 1, 2, 3, 4, 5, 6. And then on carbon 6 we have, let's see, so let's label this. We have, let's label like the 1, 2, 3, 4, 5, 6. And so on carbon 1 we still have this ester group. So let's do some highlighting here so you know what's going on clearly. This is this group here, right? And then on carbon 6, what happens is basically you attack here. Okay, so you're gonna attack here, then kick up this lone pair. This double bond is a lone pair, and this lone pair will come back down and kick off the ester. So on carbon 6, all that should be left is the ketone, right? But be careful here, because since we are in acidic conditions, we're in basic conditions here, this reagent will actually deprotonate the alpha carbon again here. So this hydrogen will get snatched by this and kick a lone pair there. So what you're actually left with is another minus charge here. So that's the product of step 1. You do have to show the minus charge in this alpha carbon, otherwise you won't get full points. Okay. And then step 2, acid and heat. So this is what you call decarboxylation. So if anybody remembers the condition to decarboxylate, you can shout that out right now. But it has to be a beta keto acid. So it's very, very important. To deprotonate, you need that. So the H3O plus, this H3O plus is going to turn this ester into OH, right? So now we have an acid here. So this is a carboxylic acid. So let's do some labeling. So if once this becomes OH, this is the alpha carbon, beta carbon, this is the beta keto, and this is the acid. Alpha, beta, keto, and this is the acid. So that's why you can decarboxylate this structure. So all decarboxylation does is it just removes that whole, this whole group gets removed. So you're left with just a ketone. Oh, and then we should also note, I'm kind of forgetting this, on carbon 3 we have this isopropyl group, so don't forget that. So it should be here as well. Yeah. And then the third step, whenever you see this P here, this sort of guy right there, this is called the Wittig reaction. So all the Wittig does is, in simple terms, whatever's on the other side of the P, so you can ignore this whole part of the thingy, whatever's on the left side is going to replace the ketone. So this replaces ketone with the carbon. So for example, we have a C H32C. So what that looks like is C, CH3, CH3. And then instead of being double bonded to P, like instead of this being a double bond to a P, you treat this P as the carbon wherever the O is. So just merge this piece into this piece. So this is now going to be double bonded to the carbon. Let's highlight the exact one. So this carbon here is this carbon here. So if you draw that, you should be left with. And you kind of have to draw tiny on this one. But it's going to look like this. And let's make this double bond more clear actually. It doesn't look that good. Like that. Okay. So that is the third reaction. So this one is kind of long, but it's probably the trickiest one. So just make sure you know the few little important things, like H3O plus and 180 degrees will do decarboxylation. If there was no heat, then this would be just OH. So keep that in mind. It wouldn't decarboxylate, it would leave it as OH. That's also a trick that she might use. I think that was on 2023 exam, so you can check that out if you need to. But that's the third one. Okay, moving on. The fourth reaction here. So we have an amine. And you should see immediately, whenever you see CH3I excess, this is going to add methyls to amine. And the goal is to make it plus charged. So what that looks like is, the product of step 1 is N, and then you're gonna have 3 CH3 groups. So 1, 2, 3. And this makes the N plus, and then you have the I minus floating around. So it's kind of tricky because this reagent doesn't make sense unless you've seen it before. So whenever you have an amine with this CH3I excess, it's trying to make a positive. Then reagent 2, Ag2O. This is kind of an interesting reagent because this also works with aldehydes. So, through the Tollens test, you can do Ag2O on an aldehyde, and that'll take it to carboxylic acid. But in this case, since there's no aldehyde, you should know this is kind of a characteristic of this reaction. This is going to do something called the Hofmann elimination. So these two steps combined, they do Hofmann elimination. I think I spelled that wrong actually. Just one F. Yeah. So Hofmann elimination. And so this will make the least subalkene. So for example, we can go two ways with this N. So we can put, if we get rid of the N here, we can kick this bond here or here. So if you go to the right, this is called the Zaitsev product. And if you go left, it's Hofmann. So that's all based off of substitution. So this is going to favor the Hofmann. So this couples and makes Hofmann elimination. And the thing is, if you didn't know that, you see it in step 3, you're using MCPBA. Now this takes alkene to epoxide. Now the thing is, if you don't have an alkene, then MCPBA is going to have nothing to react with. So if you see on the exam MCPBA, but you don't know what happens in the step before, you can, if you're like completely lost, just put an alkene somewhere and you can like kind of scavenge a few points off. But hopefully, I mean, going in, you know what's going on. That would be like in a perfect world, right? But yeah, let's put our epoxide here. Okay, so that one's pretty simple. That's an orgo-1 reaction. And then the last thing we're seeing here is CH3O Na minus, right? with an acid workup. So if you remember, whenever you have an epoxide, there's two ways to attack, this left and the right side. And the question you have to ask yourself is, how do I know which side to attack? So with epoxides, there's a handy trick, and it's called the BLAM acronym. So if you remember, in basic conditions, you attack the least subside. Then in acidic, you attack the more subside. So ask yourself, is this a base or an acid? Really ask yourself. Hopefully you said base. So since it's O minus, this is a base. The acid is a workup step. So this is a workup, not initially. Yeah. So if it's a base, which side are we going to attack? We're going to attack the left side. So if you open the epoxide, your structure should look something like this, with the OH here. And then you can put a CH2. Excuse me, this is going to be, if you open the epoxide there, then this is going to be OCH3. So this here in purple is from this reagent here. And you form a new bond. So if we draw this in our products box, it should look like, the original structure should stay, so this should stay. The OH opens up here, and then you form a new bond here. So this in red is the new bond to OCH3. And that is the epoxide opening. That's called like the basic condition of an epoxide opening. So this one's also not too bad if you know what's going on. Just make sure you remember these two reagents here, CH3I, Ag2O. They're kind of coupled, but I mean, don't show them in one step, but you should know that together they give you the Hoffman product. And you should be okay from there. Okay, now this last one, this is kind of going all the way back to exam 1. So we have, if you remember, this is called what? This is a diene. So that'll be important later. But we'll take this piece by piece. So the first step, H3O plus and 65 degrees. Let's go back to purple here. So 65 degrees, this is like decently high temp. So we'll call this high T. If you remember the little trick for this, the low temp makes a less sub alkene. And the high temp then on the opposite hand makes a more sub alkene. You can also work with like the transition states and stuff, but that was kind of too much of a headache for me personally. But if that's your vibe, then go for it. So there's a few ways we can react this molecule, but we know at the end of the day we need to form a more sub alkene. So the most substituted an alkene could be here is if we, for example, attacked here and attached an H here and made this plus, and that would, oh sorry, this would make the least sub alkene because that would leave the double bond here, right? But if we, so I'll leave that actually there. So this would be the low temp product. So this is wrong for now. But since we're at high temp, we're actually gonna do something like this. So if we attach the, if we put the H, let's see, we can put the H here, right? But we kick this alkene up here. So let's say we move this double bond here. So now we have an alkene here and a plus charge here. And this is much more substituted than this. So this is more sub. So this is gonna be the right product. So let's redraw what this looks like and the product of actually step 1. So the actual product of step 1 is going to be an alcohol. So from step 1 we get this structure, alkene here, and then an OH wherever the plus is, because that's the reaction H3O plus with an alkene. So this will, let's write that in, add alcohol wherever it adds it, that's kind of up to your discretion to realize that. If it's low temp, you make a least sub alkene, and then at high temp, you make a more sub alkene. But yeah. So that's the first step. That's probably the hardest part of this whole reaction sequence, right? But then the second step, PCC, this just takes the alcohol. So it takes a primary alcohol to an aldehyde. So in this case, we have a primary alcohol, so our step 2 is going to be an aldehyde. So that looks like this. Draw this in here. Okay. So this will just turn to double bond OH. So now you have an aldehyde, okay? Now this next step is extremely, extremely challenging. So this right here, all of a sudden, is no longer a diene, right? This is now a dienophile. But if you look up here, this thing, this is a diene. So what I would recommend you to do on something this important, like on your final exam, is redraw this structure. Okay, redraw this structure and line them up as if it was a Diels-Alder reaction. So I would draw this like my alkene would be here, and I'd have my aldehyde up here, and there'd be a carbon here. And then I would draw my this little structure right here, the pentane, kind of angled, so it would look like this, and these two would be here, and then my OCH3 would be here. So this is kind of what's going on. This is a Diels-Alder reaction. So as tricky as it looks, it's actually fairly simple. All you have to do is flip up the tip of this pentane. And so let's draw the combined structure. So this isn't quite the answer. This is like fake 3, like we're not done yet. But you're gonna draw the new structure, which is gonna be like a bridgehead. There's gonna be a bridgehead involved, basically. And we'll highlight so you can see what's going on better as well. But this here in yellow, this bridgehead, is from these 5 carbons. So that's those 5 there. And then the other, like the other carbons, these 2 in green are these 2 in green. And then you have to substitute the groups. So we know there has to be 2 methyls, so let's put those in. So methyl, methyl. And then there's also an aldehyde. So the aldehyde, if you remember, is gonna look like this, right? And then it's also important that you put the aldehyde trans to the alkene, because you want to put it basically on a wedge in the endo position, because that is more stable. So the endo position is where you want your withdrawing group to go. So that's going to be on a wedge, or sorry, on a dash there. And then the trickiest part of a Diels-Alder reaction is labeling where to put the donating group. So if you remember, there's something called the 1,4 and the 1,2 adduct. So you want to make sure that you're withdrawing and donating are 1,4 or 1,2. Otherwise, you have the wrong product. So if we call this carbon 1, then this is 2, this is 3. Oh, I went away. 1, 2, 3, 4. So the methoxy group has to go here. So this is OCH3, like this. So this actually is the product to reaction 3. So just be careful with the Diels alder. Make sure you have the right adduct. And then step 4, this Ag2OH2O-THF, this takes aldehyde to carboxylic acid. So it's a selective oxidizer. So your final product looks like this. That's the bridgehead there. And then this, still it should remain on a dash since it's the withdrawing group. But it should be a carboxylic acid now. And these two methyls remain here, and this OCH3 remains here. So this one is pretty tricky and pretty long, but I think if you get comfortable with the numbering, for example, the 1,4 adduct, 1, 2, 3, 4, then you should be okay. That's the most common mistake people make, is the numbering of the product. But I think if you get that, then you'll be set. So that's how you do the reaction section on this exam. Let's go to the mechanism now. And so the biggest thing with the mechanism is you need to always draw the most stable intermediate. Obviously don't show the transition states, but you need to draw the most stable intermediate for, I think like it's an extra one point or something. So you don't want to miss that. But on the final exam, the biggest thing to do is kind of look at your product and work backwards a little bit. So what I mean by that is, if you look at this ring in yellow, you can spot that exact ring right here. Then if you look at this methyl in green, you can spot that right there. So that off the bat tells you that you shouldn't be messing around with this part of the product that much, right? Then another thing you can note is, if you look at our product, and I'll do it in red here, 1 carbon away, 2 carbons away, so these two, there is a ketone, and you see something like that is right here as well. So perhaps something happens with this ketone that keeps it there, but at the same time there's some more reactions occurring. And then the last big thing to note, and the red one's kind of like a stretch, so don't worry about that too much, but the last thing to note is that you do form a 6-member ring. So if you start numbering, for example, like here, we need to find a way to make a 6-member ring. So 1, 2, 3, 4, 5, 6. So that actually worked out perfectly. But let's say, for example, you didn't start numbering there. Let's say you deprotonated here. So let's say you numbered this 1, 2, 3, 4. So you'd only get 4 carbons. So that means that you shouldn't deprotonate at this position, because if you do it there, right, if you deprotonate at 1 and you get a minus charge here, you get a minus here, and this reacts, or this carbonyl, then you wouldn't get this 6-member structure. You get a 4-member ring. So that's not right. That's incorrect. So that's why you kind of have an indicator that, okay, if I start here, 1, 2, 3, 4, 5, 6, I'll get that 6-member ring. So we're just gonna kind of go with the flow here and deprotonate right here. So let's draw in the invisible hydrogen, and NaOET is gonna deprotonate this, and it's gonna make a carbanion. So let's draw that intermediate. Okay. And this is C minus now. So now that we have a C minus, you have to show the most stable contributor. And that means that the lone pair from the minus have to come down and put the minus on the oxygen. Because since the oxygen is more electronegative, the minus is more stable on there. So we're going to redraw this structure, but with the minus on the oxygen. Oh my goodness. Oh, not like that. Like this. O minus here. Then the double bond is there. And then this other side of the molecule is kind of untouched. So this is still O, and then OCH2, CH3, and this methyl is still here. So this is like the double-sided arrow to show the contributors, basically. This and this, right? But now, this is the next most important part. You have to show the actual reaction occurring. So this lone pair here is gonna attack this carbonyl. And so if you number this, let's do it in pink. 1, 2, 3, 4, 5, 6. This basically makes a 6-member ring. So I would advise you in your products to just draw the 6-member ring, and then you can number it after, okay? So in our product, we know we have to have a 6-member ring like this, and we know this methyl must be here. Okay, but for now, that's all we know. So now let's label this. We know this carbon has to be carbon 4 because this didn't change, and this is 5, right? So if that's 4 and 5, then that means that this must be 3, 2, 1, and this is 6. So then off of carbon 6, what do we have? We have, and now we have an O minus, and we also have an this ether. So CH2, CH3. And then don't forget on carbon 2, we still have a ketone. So that all checks out kind of simply. So that's why I would say just draw the expected product, and then you can kind of work backwards to see what deserves what charge, basically. Now you see in our product, we reform the ketone on carbon 5 here. I'm sorry, on carbon 6. So to reform the ketone, what you have to do is draw the lone pairs here, and you can basically kick this lone pair down and kick the ketone off, or kick the ether off. So that'll leave you with the same product, methyl here, except now you have a ketone, like a diketone. Now this is where a lot of people make a mistake, and hopefully this is not going to be you guys. So you might assume that this ends right here and you have the final product. The only issue is, since this is such an acidic compound, this here, so acidic, since the alpha carbon is between 2 ketones, it gets deprotonated again. So it might seem like it's a little bit repetitive, but the OET minus is going to deprotonate this again. And this is characteristic of a specific reaction type, and that's the Claisen condensation. So you have to show this structure being deprotonated twice. Oh my goodness. So this ketone will be here still, this will be here, and we'll have a minus here, and this methyl will be here still. So you have to show that deprotonation. Now, since you deprotonated this, there's going to be a resonance contributor. So you can either kick the lone pair up here or down here. They're both fairly acceptable, so let's just, for sake of example, kick this here and kick this up here. So let's draw the resonance contributor now. And we're going to have another intermediate like this. The methyl is there. There's a double bond and an O minus. So this is just one of the resonance contributors you can show. You can draw the other one as well, but you have to show one of them to get that point. Okay, and then finally the last step is to use H3O plus to get back to this. So using this H3O plus, the well, let's be very, very clear here. This is actually H2O with an extra H, and then this is positive on the O. The minus here will attack the hydrogen and make this like this. So make sure in this molecule that you show this extra deprotonation step, because if you skip that, you will miss out like maybe 6 or 7 points just from one mistake. So you have to show the deprotonation and reprotonation. But the mechanism is honestly very repetitive, so the more exams you do, the more obvious it'll become. Yeah, but just kind of be on the lookout for these small tricks, like recognize what stays the same, and then number your reaction, or you number your carbon so you know like what's going on. Yeah. Okay, and then the worst part of this dreadful exam is the synthesis. So on your final exam, you will be doing a mycosynthesis. So that should be in the back of your mind. And the way you figure that out is through some Greek lettering. So if you find an alpha carbon, so for example, let's say this is the alpha carbon to this ketone. So that's alpha, beta, gamma, and delta. So if you have a delta dicarbonyl, then that's like ding ding ding, this is like myco. It's happening somewhere because that's a product of a myco reaction. Now the only issue is in this specific structure, you don't see the myco donor and the myco acceptor immediately. But the easiest way to get around that is doing something called the temporary ester strategy. And so I think a few of you that messaged me, you really like doing the amine strategy, the enamine, sorry. But I simply never learned the enamine strategy. So I just did temp ester. But if you like the amine strategy, I think the key also used the enamine. So it is okay to do it that way. I think that's how she did it as well. But for this specific example, I remember doing the temporary ester and she said it was fine. So I'll show you guys how to do that. So the easiest way to do temp ester is find an alpha carbon. So we can do this one or this one and just throw an ester on there. So we'll go here to this alpha carbon and let's throw an ester on here. So this will be O, and then we can say OET here. So now all of a sudden, if you look over here, what does this look like to you? This looks like the myco donor. So here we have a myco donor. And on this side, we're gonna make this in pink, the myco acceptor. So this is the myco acceptor. So let's just work backwards now, okay? So all you have to do is draw in this fake ester, but be very careful on this step here. We're gonna make sure that we do H3O plus / 180 degrees. So that's how you're gonna get rid of the ester, right? So kind of stick with me here. We're gonna redraw this whole structure, right? Like this. So this benzene is gonna be here still. And this is gonna have an ester here, like this. Okay, this is all gonna be the same. So this ketone will be here, and this will also be here, like this. But now up here, erase the ester, because this reagent will decarboxylate the ester off. So that looks like your answer now, right? So now we have to just work with this. So this looks much easier to work with. If you label this, we have alpha, beta, gamma, delta. So this is a delta. dicarbonyl. And so we can, again, call this the Michael target. So what you're going to want to do here is break the alpha and beta bond. So break this bond here and split it there. So that's how you split the Michael into the donor and the acceptor. So now we have two pieces. We're going to have this piece on the right side. This is going to look like this. And we're going to have the other ester here. So that's one piece of it. And then the other piece is going to be the Michael acceptor. And you're going to want to just keep the split the alpha and beta, and then keep everything else the same. So this is still going to be here, this is still going to be here. But after you split it, you can do a few things. So there's an even easier way actually. So you can split it at the alpha and beta, right? But if you want to actually, let's work backwards a little bit even more. You can leave the substituents on the alpha carbon. So we can leave this here and take that back and split it between the beta and gamma carbon. So you can do the other way too, but this will be easier, I think. So the alpha carbon will still be substituted here, and this carbon will have the methyl. So there'll be methyl here and this group here, like this. And then on the other side, the reason why we did that is because now we can put the Michael acceptor right here. So it'll be a lot easier. So we just do like this and this. So now we all of a sudden have a much better, much more manageable synthesis here. And the way you get to that from the two Michael pieces is you use the reagent NaOET/ETOH as step 1. And step 2, you're going to do H3O+. Yeah. So that'll basically deprotonate here, make this minus, and this will attack here, kick here, make this. And then the H3O+ will reform the structure. So now the challenge is, how do we form this and this? So we'll go with the left side first because this is a lot easier. But if this is confusing you, let's do some highlighting just in case. So this whole group in yellow is this group here. So we just kept that all on the Michael donor. You could put it on the acceptor, but it would make it like cluttered. So that's why I chose to just move it onto the donor. It's easier to work with that way, I think, too. So if we work backwards here, and we need to make an alkene, you should be, you should know a reaction that puts a bromine on the alpha carbon. And we'll work back to that. But if we have a bromine there, and we use a big bulky base, like tert-butoxide, then that can make an alkene. And then how do you make this bromine? You can do Br2 and acetic acid. So this will put the bromine on the alpha carbon. So that, you can work back to this. Okay, and then how do you form this structure? Well, this is just a carbonyl. So you can do an alcohol and PCC. So let's work back to an alcohol. And we know PCC will turn that into the ketone. And this is an alcohol of 1, 2, 3, 4 carbons. And you can start with alcohols of 4. So that's good. So we can box this side in then. So that's why I think it's easier if you keep the Michael acceptor, keep this kind of clean, because it'll get messy on the other side, but it's easier to manage with the donor than the acceptor, I think. Although both are acceptable ways to do it. So now we need to figure out how do we attach this group here that I've circled in red to this piece here. And the answer's fairly simple. We're going to split this up. Let's redraw this real quick. So redraw. And let's make it look a little more neat. So if you redraw this, it's gonna look like a benzene here. Okay, and the benzene is attached to a carbonyl. And that is attached to another carbonyl. And that is attached to OET. And then at the alpha carbon, there's this group with a methyl and a benzene. Like this. So this group in yellow here is still the same. Okay, so now hopefully you can see in a little bit more of a manageable way how we make this. So if we want to make that, you know we're going to need to do a deprotonation of the alpha carbon, NaOET. And then the second step is you can just have the same structure of a benzene like this connected to carbon like this, but we need to brominate here. So that way, whenever this this minus attacks the carbon, you can kick the bromine off. So that's how you do that. And if we keep working back, we're gonna have then C double bond O like this. And this will look like, so this is gonna be a benzene here, like that. And this is gonna be OET. So we'll pause there and we'll make this molecule now. So to make that, we need to get a bromine on that allylic position. So we can do NBS / light. And that will allow us to have this structure brominated, right? And then how do you form this structure? To form this, well, that looks like an alkyl group on a benzene, which you can get from, draw it like this. Let's say we had a ketone here. How would we reduce a ketone to an alkyl group? Well, you can do Wolff-Kishner. So Wolff-Kishner is NH2, NH2 / KOH / heat. So that's good. And then how do we attach this ketone to a benzene? You should know Friedel-Crafts. So you can do a benzene plus a chloride, acyl chloride, like this. Well, how do you form this? You need to do SOCl2 on a carboxylic acid. And how do you form a carboxylic acid of 2 carbons? Well, you have an alcohol of 2 carbons. So it should be an alcohol of 2 carbons. And you hit that with Jones. So far, we've made 2 out of the 3 pieces. So all that's left to make now is the actual Michael donor. So let's kind of make some space here. Let's move everything a little bit. Let's move this up. Move this a little bit more left here. And move this here. And we can move all of this more to the left. Let's grab all of it. So this is going to be redrawn into that. And then what happened here? Erase that. Okay. So let's refill this in here. Erase this. And then we can kind of clean up this area. Okay, so this is all here. Now we need to focus on making this piece. So to make this, you can do a few different things, but the easiest way would be to combine, split the molecule between the alpha and the beta carbon. So split it here and treat it as two different pieces. So if we split this here, and then we're left with C double bond O, OET here, and we're gonna leave this like a carbon. And then on the other side, we can do another double bond O, OET, and then we can have the benzene here as well. So this is what, like a crossed aldol molecule. And if you hit this with the NaOET, BTOH, and H0+. So that'll work there. Then we need to find out how to make this stuff. So we need to make an ester. We can make that from a carboxylic acid. So let's work back to, this is OH. Let's call this carboxylic acid. How do we do that? We hit it with an alcohol that we need. So the ET is just an ethyl. So CH3CH2 OH with acid. And so that'll work it up to the ethyl. So that'll make the ester. And then how do we make this? This is simply just another 2-carbon alcohol hit with Jones oxidizer. So that's this piece done again. And then how do we make this here? Well, we're gonna do the same thing because we want to make it into ET, so CH3CH2 OH with acid. And that's gonna take it back to an alcohol. Right? And then how do we make an alcohol? We can hit, for example, an aldehyde. Hit an aldehyde with Jones ox. So if we go back to an aldehyde, then we can oxidize that. Let's redraw that structure. So that'll look like the same thing here. So this will be an aldehyde. And you can do Jones oxidation of that. And that should work there. And then to make the actual aldehyde, you can do on a benzene co-alkyl alkyl that, and that will put an aldehyde on the benzene. And that is going to be it for the synthesis here. Let me see if there's any issues. Yeah. So the temporary ester method is a little bit longer than what she did on the key, but it just made more intuitive sense to me. Obviously, if you guys have a different preferred method, then that's totally fine. So do whatever you're most comfortable with. But this is just another way you can synthesize this molecule. And then for the last part, which is the spectroscopy, let's go through this real quick and see what's going on. So inside of our spectroscopy, the biggest thing to look out for is obviously the proton NMR. So off the bat, let's see what we have. In the 6.5 to 7.5 range, we have a 4H. So this is like the benzene range, but you can't know for sure. Let's do the unsaturation. So 2C plus 2 minus H. And then the rule for nitrogen is you add nitrogen and divide all that by 2. So whenever you do all this, you should get 22 plus 2 minus 17 plus 1. All that over 2. So 24 minus 17 plus 1 over 2 is 8 over 2, which equals 4. So 4 is the perfect number for benzene. And so the odds are you will have some benzene ring. Okay. Now you should know that 4H, this is not para. Ever. So para has to be 2H, 2H. If you don't see this, then it's absolutely not para, and you would get points off. So other than that, the ortho-meta splitting is kind of difficult to pinpoint between each other. So I think on the last exam, like on this specific test for like the dye substitution, it was 2 points. But if you put para, you only got 1 point. So be careful with that. Para, it has to be 2H, 2H. Otherwise, it's not para. So don't fall victim to that. But let's go through these splittings one by one. So first off, we have a 6H. So 6H means you have either CH3 bonded to the same thing, or it could also mean you have CH2, CH2, CH2. Now the only issue with this is, what kind of peak is this? This is what you call a triplet. Triplet means this must be neighboring 2 hydrogens, because it must be n plus 1. So that means that whatever these CH2s are bonded to, they have to be bonded to a CH2. So that being said, if we drew it like this, and we said they're bonded to the same carbon, then that means that this would be CH2. Now if you look at this structure, what's wrong? The issue is there's no more bonds available here. So that's how you knock out this possibility. So it basically, it doesn't look like this, because if this was actually CH2, then the structure would end here. It would be finished. So this can't be a CH2. So now let's look down here, what's going on here. So if we had 6 H's like this, then the issue would be that these 2 H's, well, this is neighboring 2 and 2, 4. So we would need 4 plus 1 peaks, so we need 5 peaks. But we don't see 5 peaks. So that means that this is also wrong. So what are some other possibilities? We could also have CH3 in a symmetrical molecule. So if it was symmetrical, then this and this would give off the same exact peak. So that's the only logical explanation. So this must be bonded to CH2, and this must be bonded to CH2. The only way these can give the same signal is if they're bonded to the same things in a perfectly symmetrical pattern. So that's how you kind of work through a 6H peak like that. Then you have a 3H peak in the 2 to 2.5-ish region. So this is just going to be a CH3 bonded to nothing. Like it can't have any, like CR2 basically. Yeah. Or CR3, sorry. So it can't have any hydrogens, because n plus 1 is 1, which means that n must be 0. Okay, then you come over here and you have a 4H peak, and this 4H peak is a quartet. So n plus 1 equals 4. If n plus 1 equals 4, That means that N equals 3, which means that this is CH2 and they must be bonded to CH3s. Now the thing is, this is a 4H and this is a 6H. So if you think about these two signals respectively, these are reinforcing each other. So this is a reinforcing signal. Because this 6H tells you about these two, and this 4H tells you about these four, right? So then you know you have, okay, another CH3, another CH2. So this here in pink, this here in pink, okay. And this in red here is this in red. Okay, but now something interesting is going on. And that's the fact that this is in the 3 to kind of 4-ish range. So if it's in the 3 to 4 range, that means it's bonded to something electronegative. Now, what are our options? Our only option is a nitrogen. So for now, I'm just gonna bond them both to a nitrogen. And this might be wrong, but we'll fix it later. So that's bonded to a nitrogen, okay. This piece is done. We still need to deal with this 3H. Now, if you think about the benzene substitution, the benzene has to be disub, because look at this splitting. There's 2 peaks. So there's some kind of disubstitution going on in the benzene. So you can kind of guess and check an answer. Let's say we have a benzene like this, an N, and it has an ethyl here and an ethyl here, like this. And that would be okay. And then the CH3, this could just be a CH3 on the benzene. So you can just put a CH3 here. And this would be the ortho product. I think she did accept the ortho product in this exam. But her key might have the meta product, but they're both technically acceptable. But yeah. So that's all you need to know about the spec here. It shouldn't be too crazy, I don't think, especially because you're so limited on time. If you don't know the general structure, so I'll paste an image here that we can kind of look at together. So you can kind of ignore some of this stuff, but let me show you what to look out for. So we'll go to the top. Oops. Let's delete this page. Let's add a page before. Sure. And let's put this picture here. So this is what your final exam actually is going to look like structure-wise. So you're going to be given that ACS exam, and you're going to be given 55 minutes to do it. And then your actual exam, you're going to kind of get the ACS exam taken 50 minutes. After 55 minutes, you have no choice but to turn that in. Then you have to turn in the exam by 9:50. So you have about an hour on both targets. You should aim to finish the ACS exam as quick as you can, though, because then you can kind of jump into the bean exam. So once you finish the ACS test, then you start the bean test. And then you don't have like infinite time to work on both, basically. So I'm sure she broke this down for you guys in class as well. But for anybody who's lost, you're going to start with the ACS test, do around 36 questions. It says covers Orgo 1 and 2, but I think there's like a heavy emphasis on Orgo 1. But definitely just look through everything. And then the actual final, I think there's a similar breakdown. I don't know if you guys have facts or not. Yeah. Oh, actually here it's saying you don't have facts. So that's perfect. That's good, yeah. So this is how your exam will be looking, basically. So some final words of encouragement. You guys got this. Good luck to you all. And if you have any questions, you can message me on Teams or group me, whatever. And hopefully, you all crush it. So, good luck, and you guys will do wonderful.